Hello everybody, let's do this. This is lesson number 3, types of discontinuities. The game plan today is, what does it mean to have a discontinuity within a graph, and how can we find discontinuities without looking at the graph? So this lesson will be very nice. Let's do it. So here, before we even start anything, the class notes that I'd like you to have down, I wrote down nice and neatly over here. So what I want you to do is pause the video, have this in your notes, pause the video, have this in your notes, and then have this in your notes, pause the video, right, let me move my hands, right? Okay, next one, infinite discontinuities, and this one I need to complete for range, but domain, let's have, okay? All right, so imagine that I'm guessing you have all your notes written down before you continue to the next part. Let's just review this first one together. Here, lesson 3, types of discontinuities. So jump discontinuities. The graph of f of x is shown below. So we have some graph and we're looking at x equals a, right? A is any x value. The function is approaching different values from the left and right. When this happens, we say we have a jump discontinuity. So the idea is, notice that for this little example here, that the limit of f of x as x approaches a from the left, what is the y value that it's going to? It is L. And for where is it going from the right side? It's going to M. Notice here the question, the limit of the limit of f of x as x approaches a in general. So you notice from the left it's going to L, from the right it's going to M. From the left and from the right they're going to two different locations. What do you know about the limit in general? The limit does not exist, right? If it were to exist, it would have to go to the same location, and notice that it does not. So it's very important to connect that for jump discontinuities, the limit does not exist, okay? Here, for the next one, for infinite discontinuities, the idea here is the graph shows a function that is discontinuous at x equals a. The arrows of the function indicate that it will grow infinitely large as x approaches a. So the idea here is, if the limit as x approaches a from the left at f of x, so the limit of as x approaches a from the right of f of x, notice that these are, from the left it's going to infinity or does not exist. And same thing over here, it goes to infinity or does not exist. So whenever we have the limits going to either the positive infinities, or it could be, one's going to the positive, one's going to the negative infinity, they're both going to the negative infinity, it could be the other way around. Whenever we're going to the infinities, we're going to say we have an infinite discontinuity, okay? All right, and let's look at the next part over here. The type of discontinuity will be a removable. So here, removable discontinuities, in the graph below, there's a hole in the function at x equals a. Wait, I should have an a over here. These holes are called removable discontinuities. So let's take a look at this graph. If I said that this graph was f of x, right? Notice what's happening for the limit of f of x as x approaches a from the left. What is happening of f of x as x approaches a from the right? Notice that for both of these, from the left it's going to L, and from the right it's going to L. So the limit in general of f of x as x approaches a, the limit in general is still L, right? And notice that the limit exists, okay? The limit exists over here. And the same concept is going over here, that from the left and from the right, it's going to L. But let's say this graph is g of x, right? We know that the limit of g of x as x approaches a, it's going to be L. But the most important thing is it exists, okay? All right. So that's going to be really important to connect that for a removable discontinuity, notice the limit will exist, okay? All right. So let's actually try and go through one together. So here, let's do the first one together. The idea is for A, B, and C, what I'm asking you to do is, let's look at the graph, and I want you to identify at which x values represent a removable, a jump, or an infinite discontinuity. So let's have a little fun. Let me zoom in a little bit. Okie dokie. So my bad. Let me make this nice and neat. Let me fix the resolution. Let me get my very nice pens going. All right, we got the stabilos. Okay, so let's imagine we have our favorite person in the whole wide world. We have Super Mario. Okay, so we're gonna take Super Mario, and Super Mario is just gonna go on the graph. So notice that at x equals -9, Super Mario could start at x equals -9. Okay, so notice that if this is Super Mario, da 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 da, right? And it just kind of like goes, right? So here Super Mario is going, and notice how I'm not picking up the pen, right? So Super Mario keeps going. There is no discontinuous break. We have Super Mario at x equals 9 is okay. X equals -8 is okay. -7 is okay. -6 is okay. -5 is okay. -4 is okay. But now that I'm getting closer and closer to -3 coming from the left, notice that if Super Mario just keeps going up, up, if I keep getting closer and closer to -3, he will never get to this side of the graph. For Super Mario to be able to actually go to this side, we need to pick him up and bring him to the right side of -3. And notice the idea is the second you pick up your pen, a type of discontinuity will occur. And the question is, what type of discontinuity is happening at x equals -3? Okay, pause the video and try and find out. Here, this one's a little bit straightforward, but the idea is it's an infinite discontinuity because as the limit as x approaches -3 from the left and from the right, it's going to the infinities. So here, at x equals -3, we have a infinite discontinuity. So over here, at x equals -3. Okay. Now let's keep going, right? So now we take Super Mario. He's over here, and we go la 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 la. At x equals -2, we're okay. -1, okay. X equals 0, we're okay. But now let's see, we're getting closer and closer to 1 from the left. Notice for Super Mario to get to the other side of the graph, we have to pick up our pen. And the second that happens at x equals 1, what type of discontinuity do we have? Same idea. We have an infinite discontinuity. So here, for infinite discontinuity, we're going to write x equals 1. Okay. Now let's continue. So we're over here. La 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 la. X equals 2, we're still okay. X equals 3, we're okay. X equals, oh, what's happening here? For Super Mario to continue, what is he doing from the left? He's going here, yahoo, and then back. But notice that he can't jump to this hole. Notice that what did we do to go from here to here? We had to pick up the pen. And the question I ask is, what type of discontinuity just occurred at x equals 4? What I want you to do is pause the video and look at your notes and see what type of discontinuity occurred, right? So let's say you're coming back to the video. This type of discontinuity is a removable discontinuity, okay? Now, some of you might be saying, oh, mister, you jumped, right, from here to here, and that's what I was thinking. But here, the most important thing is between the we knew this wasn't infinite, right? For sure it wasn't infinite. But let me just make this very, very clear. I said it in the notes as we were going through it. For removable, the limit exists. Okay, when a limit exists and we have to pick up our pen, a removable discontinuity occur. In this instance, where we have a jump discontinuity, the limit does not exist. Okay, so my question to you is over here simply, does the limit exist at x equals 4? So the limit of f of x as x approaches 4, does this exist? And the answer is yes, because the limit from the left and the limit from the right are both going to -2. Okay? Don't get thrown off because this little jump thing. What I want you to do is think of limits. If the limit exists or the limit does not exist. So here, this is at x equals 4, we have a removable. Okay. Now let's zoom in a little bit. Okay. And now we're Super Mario, so we just did a little jump here. We did a little maneuver to get from here to here. Now we're going, stop. Now you're Super Mario, you gotta get to this platform, right? Notice what type of discontinuity occurs here. Pause the video at x equals 6. What do you think? Pause the video, right? Now you're coming back to it. This will be a jump discontinuity, and the reason is the limit does not exist because the limit from the left is different than the limit from the right. And that's the definition of some sort of jump discontinuity. So we know at x equals 6, we have a jump discontinuity, okay? So, very nice. What I want you to do is, if this felt okay, try and do, let me zoom out a little bit, so you have page 2, or you have question 2, question 3, question 4, right? What I want you to do is do A, B, and C. Find all the removables, jumps, and infinite discontinuities within this graph, if they exist, right? And what I also want you to do is, if you say, for example, at x equals -2, right? So let's say here, whichever type of discontinuity you think is here, I want you to write y. Whichever type of discontinuity occurs here, I want you to write y. Explain in words why a certain discontinuity is occurring, okay? All right, so I'm gonna pause the video and, you're gonna pause the video and try and do this example, okay? So let's say you pause the video and you wanna come back. Let's take a look. So here, this one's a little not too bad, right? So here, Super Mario is here, We're all good. Oh, x equals -2. What type of discontinuity do we have? This will be an infinite, right? What's the reason why? We are going, well, we shouldn't say we, the graph of f of x is approaching infinity as x gets closer to -2 from the left, okay? All right, you see how technical and nice this explanation was? Yeah. Okay. So let's say we have this infinite discontinuity, x equals 3. What's happening at x equals 3? This will be a removable. Why? Well, because the limit of f of x as x approaches 3 is equal to 2, and most importantly, it exists, and f of 3 does not equal to a removable occur. Now this was a little, I didn't expect you guys, we didn't really talk about this, but what this is saying is, notice that the limit is going to 2, you're saying, notice that the limit is going to 2, but what is f of 3? What is f of 3? It's not 2. So if f of 3 is not 2, but the limit is going to 2, that's implying there's a hole here. It's implying that there's a hole, okay? I know this was a little technical of a definition, but we'll get better at handling this. Okay, next one. So x equals 3. What's the next one? Here, x equals 5. What I want you to do is pause the video and try and give an explanation very similarly to what I have over here. Why is at x equals 5, there's a removable discontinuity, right? Here, the limit, and if you pause the video and you want to see the limit of f of x as x approaches 5, it's equal to 3. But notice that the limit of f of x as x approaches 5 does not equal f of 5. Okay? Because here at f of 5, what is f of 5? F of 5 is undefined. There is no y value. What is f of 3 actually over here? When you plug in 3, notice that f of 3 is 0. Okay. Oh shit, sorry. Oh, my bad. I did not mean to say that. But here, that's what I wanted you to see. Okay. Here, that's done with this. All right, so let's take a look here at x equals 6. Here at x equals 6, we have a jump discontinuity. So at x equals 6, we have a jump discontinuity. And what's happening at x equals 6? The limit, what's the explanation why? The limit as x approaches 6 from the left of f of x does not equal the limit of f of x as x approaches 6 from the right. And notice, look how nice that explanation was. I'm saying the limit from the left does not equal the limit from the right. Okay? And at x equals 6, there's a jump discontinuity. And then from here, we're good. Okay. For here, what I want you to do is, if you finish this page, what I want you to do is take your time and try and write an explanation for each one. What I'm going to do is, I'm just going to quickly go over the answers. So here, at x equals -6, here we have a jump. At x equals 0, we have a jump. At x equals 5, this is removable. And at x equals 7, we have a jump. Okay? And there are no infinite discontinuities. All right. Let's see the next one, question 4 here. At x equals -7, we have a jump. At x equals -6, we have a removable. At x equals -3, we have a removable. At x equals 3, we have an infinite discontinuity, and then here we're good. Okay? All right, so that was the first part of the video. Notice that we did A, B, and C, right? So we talked about the removable, jump, and infinite discontinuities. For the next video, we'll talk about the domain and range. And this won't be too bad, you just need a little bit of practice. Okay, I'll see you.